Hello and welcome to Unit 9B. This will be the last one for this one, I hope. And we talked about the inside and the outside of the sun, and we're going to add more to the outside. This is actually a picture from spaceweather.com showing what's called a coronal hole. And basically what happens is the corona protects the Earth or the rest of the solar system from solar wind being pushed out by the photosphere, the chromosphere, um, and if they get a hole in the corona, we have solar wind pouring out of there. So if we had a coronal mass ejection around a hole or a solar flare inside of a hole and it faced the Earth, we'd actually have a big problem. So let me just see if I can open up space weather. Okay, and here's the picture of I'm going to show this to you later in this show. If we go down a little ways, and I missed it. Where's the coronal hole? Okay, so here's what the coronal hole looks like today. And you can see it's, instead of going equatorially, it's going sort of in a polar area, but it's still facing the Earth. So if we had a pretty good opening right there, we would have some issue. Okay, so here was the nice hole, and you can see it is more equatorial, and now it's more polar. Maybe this one opened up and maybe this one came down, I don't know, but you can see there are quite a few holes, very large holes, very nice sized holes. Okay, these are sunspots, and if you take a look at it, the sunspots on the equator actually move faster than they do toward the poles, and this causes issues with prominence. Sun undergoes differential rotation. The rotation period of the sun varies between 25 days around the equator to 35 days near the pole, and it actually averages up to 27 days. And the reason being is if you take a look at how much material is the polar and how much is the equatorial, there's a lot more area in the equator moving at 25 days for 360 degrees than there is for the poles, actually turning 35 days. So we're going to say the average is a 27-day rotational speed. Therefore, magnetic fields on the sun become intertwined. And I want you to try to draw as many of these pictures as you need. It looks like they start off in a nice straight line, but because the equator moves faster, this area pulls out in front and can actually lap the rest of it, and it actually equates out to these large areas, and then it starts forming these inconsistencies, these little loops where the South Pole goes up, the North Pole goes down in the Northern Hemisphere, and the South Pole goes up and goes down on the North Pole for the Southern Hemisphere, but it seems to move in a clockwise direction for one and a counterclockwise direction for the other. But that's what produces these prominence. They're magnetic waves that actually move material from the photosphere and the chromosphere up into the corona and then come back down. And I would like you to draw whatever you need to get these two images, and then finally to make this prominence, but you can actually draw that in this diagram. Sun's magnetic field creates different features in solar wind. Sunspots, areas of concentrated magnetic lines, which produce solar wind. Prominence, magnetic loops above these sunspot areas can carry plasma, hot ionized gas, up into space. Solar flares are twisted magnetic field. When they get even more twisted, they actually relax and release huge amounts of X-rays with solar wind. And then the coronal mass ejections, the CMEs, which are twisted magnetic fields, even more twisted, and these lines relax and release huge amounts of plasma that can travel up to 404 million miles per hour, making it to the Earth in a couple of days. Sunspots. I would like you to know it's got two regions. It's got what's called the penumbra and the umbra. Same thing we talked about with eclipse, for a total eclipse or a partial eclipse caused by the fuzzy part of the shadow and the dark part of the shadow. Terminology for sunspots works out the same. They can be overlapped, but you can still start seeing the darker areas, but darker and darker. These magnetic areas actually are intense, formation of intense magnetic fields, and you can see that I'm not going to get into the physics of this, but basically they come out of one spot and they go into another. Sunspots viewed in different wavelengths of light, same as we viewed the sun earlier, showing you more definition in some of these wavelengths than there are maybe in others. Not sure what actually is being shown in this green one. Number of sunspots in the photosphere varies over an 11-year cycle. Maximum sunspot, the sun can look like this, and I really wish it would look like this on my final year, and I could take you out and show you sunspots like that. Minimum sunspots, where we actually may not get any for a 12-month period. And this is what the sun looked like today, and today is the 26th of February, and I'm going to go out tomorrow and actually look at this sunspot. Actually, maybe I'll go out today and look at this sunspot and see if we can go out tomorrow or the Wednesday, either Monday, Tuesday, or Wednesday this week, and actually see this sunspot. So I will go out right after we finish this presentation. This is what it would look like if we actually, this is called the butterfly display, but if you look at the equator doesn't really get a whole lot of sunspots, but as you move up to 30 degrees, 15 degrees, you get the most sunspots, and I'm actually picking on this one because it looks like this butterfly wing is the most. And if you take a look, the most sunspots, which is actually saying a half a sunspot forming every day, that is 1957. That was the year I was born. In 1957, the year I was born, the maximum number of sunspots. Pretty cool. But between 11 and even sometimes the 22-year cycle, if you look at every other one here, they seem to be bigger than the ones around them. So there's even a cycle inside of the cycle. I used to have my earth science kids do these, and I may actually have my astronomy kids this year do a graph that's similar to this, and you can actually see these cycles. Sunspots can be used to determine the rate of the sun rotation, so we can't really see the yellow section of the sun rotate, but we can actually see the sunspots, the darker, cooler 5,000 degrees C versus 6,000 degrees C. And you can see between November 9th and November 19th, you can see these things actually move across the surface of the sun, actually showing you that it is moving. And this is a little lower than the equator, which is why it has the sunspots. I'm going to let this one just run for a second. This is amazing amount of material being thrown off onto the sun. These guys are called prominence. They're very prominent features of the solar atmosphere. And it's ionized gas trapped by magnetic fields, again, in between, like sunspots. And they arc far above, and they can be what are called closed prominence, or they can be open prominence. They can be very large. I'll give you some idea of the size of the Earth. Remember, 110 Earths go across the sun. So they can actually move out very far away from the sun compared to the size of both the sun and the Earth. Here's a picture of it through the hydrogen filter, showing you the pink chromosphere, and then there is a prominence. You can see sort of spicule-like things over here, moving up and forth. You can see granation through it, through the photosphere, into the photosphere, but you can see these large jets of gas being pushed up by sunspots. Huge violent eruptions called solar flares produce X-rays. This is actually, I think, Mercury moving across, transiting across the surface of the sun. And you can see granation, you can see sunspots, you can see the prominence that they're creating. But it also produces what are called solar flares, and solar flares can actually produce large amounts of material going off. And then we have what are called coronal mass ejections, so CMEs. And this is actually visible because we made a man-made total solar eclipse, and what we did is we put a disk in the telescope that actually covers the size of the sun, which is shown with this white circle, and you can see mass just being thrown out. CME coming out right there, that's a coronal mass ejection as opposed to just the regular ejection lines throwing out high energy plasma, which it actually ends up being solar wind. We have newer models showing more definition. Here's a picture of one that happened in March 2011, and you can see the way it looked in an old satellite. And this is a newer enhanced version showing you a lot more detail of the material that's going out. Our sun does produce coronal mass ejections, and this occurs when these magnetic fields get twisted into like a snake S-type shape. And when the S's actually go past each other, they make a connection, which actually throws this material out into space. This material does throw out maybe 2 times 10 to the 12th. That is 2 billion tons of plasma, and kicks it out more than 4 million miles per hour. And if it's actually faced toward the sun is faced, the hole is facing toward us, and we actually get this solar wind. This is not to scale. But remember, we do have this protection from this magnetic field, which moves the solar wind up and around, moving some in for those beautiful auroras, aurora borealis, aurora australis that we can view on this Earth. Following these trails, we can actually get an idea of a spiral type layer of the Earth. We can watch the coronal mass ejection move out of the sun, and it moves out, and you can see it goes past Mercury, past Venus, and actually will hit the Earth. So even if it's right there, it may not move towards the Earth. It may actually move, and we'll need one that actually goes off that direction to actually strike the Earth. This is the equation for nuclear fusion that goes off in the core, and under very high temperatures and high pressures that we get inside of stars. We take 2 hydrogens and we fuse them together, making a hydrogen 2. What it actually produces is a neutrino, which moves out, has no mass. It actually makes what's called a positron. It's a positively charged electron that combines with a negatively charged electron to annihilate each other, and it produces gamma rays, photons. And then this actually comes and fuses with another hydrogen, making what's called helium-3, which produces another gamma ray photon. And then 2 of these hydrogen helium-3s come together to make helium-4, with a byproduct of 2 hydrogens to move back into this process for step 1. So step 1, taking 2 to put together to make a neutrino, which goes off, and then 2 gamma ray photons. And then we get that with another hydrogen, step 2, to actually produce helium-3 with a gamma ray photon. And then we get 2 helium-3s coming together to make helium-4 with 2 hydrogen, which can actually go back and do this. And we lose a little bit of mass, as you can see, going out here. And this is what E is equal to mc squared. Energy is equal to mass lost times the speed of light squared, 186,000 miles squared, times the mass that's lost, produces tremendous amounts of E's. Here's the picture in a shock wave. I'm just going to let it run. So we made our 2 helium, and then we're going to make our hydrogen, and now we're going to make helium-3, and you can see material flowing off. Then we're going to take 2 of those, slam them together, and produce helium-4 with 2 protons going off into space. Okay, sun's interior is held together, or held by a very stable force called hydrostatic equilibrium. And basically what it means is the pressure forces of the sun which push out equal the gravitational forces that pull it back together. And what happens is we get these 2 arrows actually leveling out. It's the same sort of thing that this fish deep down in the water, it's got tons and tons and tons of water pushing down on it, but it also has tons and tons of water pushing up, and then we just have the weight of the fish, which is very small compared to the weight of all the rest of this. So I would like you to draw this, and all you have to do is just draw a circle and actually make 2 arrows. If you can make them offset a little bit and just make them the same size, this is what's called equilibrium. If the sun actually produces a little bit more heat, it will expand, which will actually mess up the equilibrium. But then what will happen is that the pressures inside, which create the heat, decrease. The sun will cool, and it will shrink back down to its equilibrium side. If we actually get larger stars, we can get this larger equilibrium. but the sun itself will pretty much stay the size it is as long as it's doing nuclear fusion the way it's doing it. And we are at 15 minutes, so I got to finish this. I would like you to draw this. This is showing you the core, the radiative zone, the convection zone, the photosphere, the chromosphere, and the corona, all of the layers of the sun that we're responsible. And then what do you think? Does the mass of the sun compare to the rest of the solar system? Pretty much is all of it, 99.85% of the solar system's mass. Are there any stars closer to the Earth than the sun? No, sun is the closest star. Does the sun have a solid liquid interior like the Earth? Not really. It's mostly composed of hot gases, which can be solid, can be liquid, but it's nothing like what we experience on the Earth. And this is solar wind being made visible with visible light streaming out from the sun, which is over there. And this was another prominence forming on the sun. What is the surface of the sun like? Horrible sentence. Sun has no solid surface. It has no solid or liquid anywhere. The surface we see is composed of hot churning gases. Does the sun rotate? Yes, it does. 35-day average near its poles, 25 by its equator, so it's an average of 27-day average rotation. And then what makes the sun shine? Thermonuclear fusion producing photons, which allow us to see it as well as feel its heat. Okay, that's it. And that was 1645. Adios.